Recording. Okay, so good evening all and welcome again for this training program. So let us quickly review that what we have discussed so far. So out of 25 modules, we have discussed module number 1, that is for the introduction, module number 2, that is for the equipment selection and sizing rating calculations, module number 3, that is for the transformer, module 4 for the single line diagram for the AIS type service station, Module 5, that is the SLT, but that is for the GIS type service station. And module number 6, cable selection sizing. So far we have completed module number 6, 6 module, right? And today we are going to discuss about the module number 7. And what is the class day number? 38, 37. Could anyone confirm the class day number? That is 37. 38, I'm not sure. Please, could anyone double check this? Okay, so coming to the module number 7, the overall site installation layout drawing preparation for the service station, right? So, any query, any doubt so far from module 1 to module number 6?
I think that is class 36 or 37.
So, today class day 37 as well.
Yes, sir.
Okay, thank you. Thanks a lot. Okay, so let us start module number 7. So, the module number 7, that is very much important topic in case of the service station because during the previous module number 2, let me like just quickly give you the uh, like review. So module 1, that is only the introduction that we have discussed, and we have discussed the common design parameters, right? Common system design parameters, and we have discussed about the like selection parameter for the equipment, the common selection parameters. In that we have discussed about uh, the current, the short circuit current, the lightning impulse voltage, the switching impulse voltage, the power frequency over voltage. So these all things we have discussed during the module number 1, right? Then module number 2, we discussed about the equipment selection. What is the selection criteria for the each equipment that we use in the substation, and then their rating calculations, right? Module number 3 again, equipment, but that is the transformer equipment, because transformer is one of the main equipment that we use in the substation. That is why we have to keep a separate discussion for the transformer, separate module for the transformer. And then in module number 4, we discuss about the uh, bus bar scheme, about the equipment interconnection sequence, right? In module number 4, module 5, again the equipment interconnection sequence, but that is for the gas insulated switchgear. Means we have the SF6 gas environment, and in that environment, how we are interconnecting the equipment, so that we have discussed in module 6. So only the equipment interconnection sequence we have discussed, and the bus bar schemes, right? Module number 5. In module number 6, if we are using the cable to interconnect to equipment, or some part of the equipment is outdoor and some part of the equipment is indoor. For example, we have a 33 kV or 11 kV HT indoor panel, and we have a transformer which is placed outdoor. So from the HT panel which is indoor and to the transformer, we have to take the cable. So for that cable, like selection and then sizing calculations we have discussed. So nothing, so far nothing we have discussed about the construction, site construction, because from these discussion, the nothing can be done at the site. Am I clear to all of you? Is it making some sense?
Yes, sir.
But when it comes to the construction at the site, then what the drawing, the site engineer required, right? So like first of all, the civil activity will be started. So for that they require the foundation layout drawing, they require the earthing layout drawing, But to prepare the foundation layout drawing, to prepare the earthing layout drawing, first of all, as a design engineer, we have to prepare the overall site installation electrical layout drawing, and based on the electrical layout drawing, the civil engineer will prepare the foundation layout drawing. But when it comes to the substation, in that case, the most of the equipment is the electrical equipment, or we can say the total electrical equipment. So in the substation, the main lead engineer would be the electrical design engineer, and based on that the other department will follow, will do based on that, based on their design. So even though foundation will be required, will be done at the site first of all, but when it comes to the engineering in the office, so first of all the layout drawing need to be prepared. So today we are going to discuss about that equipment installation layout drawing preparation. Okay, and this is too much important with interview point of view as well. So please focus. I need all of your 100% attention, right? So please, like, open your listening ears. Coming to model number 7. So let us again cover what we have discussed. So far in model number 2 and 3, we have discussed equipment selection, what type of equipment we are going to use, that selection, equipment sizing calculations, and sequence of equipment interconnection in the substation compound in model 2 and 3. Equipment model 4, we have discussed the bus bar scheme selection. Why? Because all circuit feeders will terminate on the common bus bar, so due to that reason we discussed the bus bar selection scheme during module number 4. In module 5, we have discussed the GIS type substation and GIS building layout, that what should be the building height, what should be the building door, right? How many floor building, or what should be the basement height, what should be the building width in case of GIS. So that all we discussed during module 5. And now in module number 7, we are going to discuss the AIS air insulated switchgear, AIS type substation equipment installation layout drawing preparation. So that is the agenda for the module number 7 and for the today class. Am I clear with the topic, that what
Yes, sir.
we are going
Yes,
to
sir.
discuss and what is the significance of this discussion? What is the significance, right? If you made any mistake here in this layout drawing, your each and every drawing will going to affect. So we have to be careful during the installation layout drawing preparation. So what I did here, I took different site photos. So this is like surge arrestor. Here I took the another equipment, that could be a wave trap,
Wave trap.
that could be
Yes.
any air core reactor. So surge arrestor, wave trap, disconnectors, CT, breaker, transformer, all different equipment we are taking from different manufacturing company. They dispatch their equipment at the site, and at the site we interconnect the equipment with help of the tube or the ACS or conductor, and we make one proper substation or one proper switchyard. So this is the agenda, means the equipment, the name is equipment installation. And what equipment, that already we have decided during module number 2. Equipment selection we have done, equipment sizing we have done. In SLD, during SLD, the equipment sequence of interconnection we have done. Now we are going to do that when we are putting the equipment on the site. So what should be their putting arrangement, what should, how we decide that where this equipment need to be placed, what should be the equipment height above ground, what should be the uh, foundation depth below ground, what should be the equipment to equipment spacing. So these all things we are going to discuss, and I need all of your the 100 percentage focus and 100 percentage concentration. since this is too much important topic, that is the reason, right? So I have during my presentation I have taken many site photos, many site pictures, including the 3D view. So we'll try to understand fully in detail, in depth, right? So the equipment, the outdoor equipment installation drawing, the outdoor equipment installation layout drawing for AIS substation. This is a 3D view where we have let me go to this view. So this is our a reference 3D drawing that just we are following. So here this is a overall site installation, overall installation we have done, right? So we are going to discuss about these equipment installation layout drawing preparation. So the point is that the equipment installation layout drawing include two types of the drawing. Means when we are going to make the installation layout drawing, we have to prepare two drawings. The first is the plan drawing, which shows the top view of all equipment what we are going to install, the top view. So based on indicating the top view, we and spacing between the equipment, we prepare this drawing. The top view of the equipment drawing name is plan layout drawing, and the second drawing is the section drawing shows or indicate the side elevation view, the side elevation view of all the equipment that we are going to install, their side elevation view. So in the side elevation view, we can also measure their height. We also need to indicate their height, that what is the height of those equipment. And why we are taking side elevation view, why we are not taking the front elevation view? Because the equipment that we are going to use RYB phase, and equipment in each three phase would be the common. So due to this reason, mostly we take the side elevation view. What I mean to by this statement, that if you come here, if you stand here, and from here you look at this circuit breaker, so you can see all three breakers, and that view will be your front elevation view because you are standing in front of the equipment. But in the side elevation view, you are not going to stand on the front, you are going to stand on the side, one side, because RYB phase is the similar equipment we are going to install. So if we indicate only one drawing, only one equipment, that also would be enough. So in the layout drawing, we need to prepare two drawing, plan and the site elevation drawing. Site elevation drawing, a section drawing which showed the site elevation view of all the equipment, and the equipment that needs to be installed shall be considered during the single line diagram preparation. So usually it is like generally we prepare the SLD. During the SLD we decide what equipment, what is the sequence of equipment, what the rating of equipment. These all things we do at the SLD stage, and thereafter we come to the layout stage. But SLD, without completing your layout, SLD is not uh, could not be approved, or it is not fully approved, because during the layout you will decide that if you are going to do the installation at the site, so what should be the sequence of the bay, and if your in the layout, if your bay sequencing is changed, so that need to be changed into SLD as well. So usually we try to prepare SLD and layout drawing all together. Am I clear? Am I clear with
Yes, actually, you
with
are
the
saying that we prepare SLD and layout drawing all together
yeah,
because
means
in case the
you can go first SLD, means you start first SLD, make your SLD
yes,
first, decide your equipment rating, equipment interconnection sequence, and then come on the layout as well. Prepare the layout as per your SLD, and if your layout is also okay, we can install equipment at the site without any problem, and then the SLD will be finally approved. Means that
Yes.
it will be final. So first SLD, after the SLD without layout, SLD is not 100%. We cannot finalize. That maybe need
Yes.
to be changed in the future if your layout changing. In that case only, I need the
Actually,
full.
this thing occurs in Postbed. That thing I want to ask.
Yeah, yes, yes.
Oh,
So one more request from all of you 38. I need the full attention because I'm going to give my.
actually, in my organization, there are different set of engineers for pre and post. That which I have observed. So that is why I was asking.
Yeah, yeah. So that all things is the post. Okay. Then detail engineering at the stage of the detailed engineering. Okay, Ashwin. Yeah.
Yes, sir.
And one more request again. I need the full focus and full attention from all of you because I'm going to give my 200% energy. So I need your again 200% of the focus. Okay. So coming back to the. So please be concentrate. So yeah, I think the topic significance is clear that I tried to explain. Right. So let us see one example. Here we have a solar substation, and this is the solar model that you can see here. And this is the actual site installed, constructed, erected site where each equipment is erected, constructed, right? So to do this erection of this pulling substation, first of all we have to prepare this kind of the drawing. This kind of the drawing means we are preparing the layout drawing where we are indicating the transformer. That now you can see this is the top view, and the plan layout drawing, which is the top view of the equipment, means we are looking these equipment from the top, right? So if we look the equipment, suppose we look this CT from the top, so this will visible as the
Like circle.
as the
Yes.
circle only, right?
Yes.
So here in the plan layout drawing, we are indicating all equipment top view, plus we are indicating the distance here. This could not be too much clear in this sketch. Have we will refer the actual sketch and actual spacing later on, but just to make you the clear that what we are going to discuss and how it relate. So first we prepared this kind of the plan layout drawing, and then we prepared parallelly. If you see A and A, means we are taking this section from this position, and as I told, side elevation, not the front elevation. So if you stand here, if you see in the front, you can see all three faces, but we are taking side elevation view, and that we indicate through the section elevation drawing. So this is section AA, and we are standing in the side, means over here, and then we look at the equipment. So we can see instead of three phase only, we can see the single phase equipment, and here we can see the height of each equipment as well. So first of all, in the office we prepared, the design engineer need to be prepared this two drawing, and then this two drawing take approval from the client consultant, EAG, whatever your approval agency, and then we send this site finally at the site. Site engineer also will need to study this drawing, that what drawings have come from the office, and is it feasible at the site. There is no any constraint during the construction that may come. So after that they can start construction, right? And along with this drawing, the site engineer need to also take the foundation layout drawing and matching both the drawing, and then they can like give instruction for the digging of the soil and the foundation preparations. Right, so left hand side is an example of the layout plan and section drawing for the site construction and installation, and the below photo is an example of the site installation. Both is not the different, both is not the same, so do not try to match. Both is the drawing, or this drawing and this site photo is from the two different sites, so there might be some mismatch when you are going to like match each equipment. For example, here we have two trafo and here we have only one trafo, right? So there might be some, but idea
You have
is,
written that that both photo may be different, but you, in nutshell, you are trying to say that this substation can be described in terms of this layout plan.
yeah, layout plan and section, right? I have given this disclaimer because later on, if you are watching the recording
Yes.
and you try to match, and then there might be some confusion, so that's why I put this statement during the presentations, right? So now coming to the uh, final drawing preparations. So when we start the drawing preparation, what the input we should have, or what the information we should have before starting the layout drawing preparation. So the first information, since you are going to make the construction at the site, so you should know what is my site land availability, what is the total available land length and width where the substation shall be erected or constructed. And for this input, how we can take this input. For that input, if you are working for any grid substation, right, in that case, for this input we can refer to the document name called as contour layout. This contour layout also called as plot plan layout, which shall be provided by the client as an input to the EPC company. So if you are a designer of an EPC company, then this contour layout or plot plan layout will be provided to your company, or you can ask client to provide the contour layout. Contour layout means the outline layout of the substation proposed site. Am I clear? This contour layout,
Yes,
land and width.
actually, developer or client gives us this
So,
control layout.
yeah, so for that they will do the survey. They will,
Actually, one thing I want to ask that contractor is different and developer is different, and developer is often act as a client. So actually, developer plans everything,
yeah.
arrange
In
finance
that,
for this
yeah, in
project.
that case, the developer will provide you, and they will let you know
And
that.
do they do that from developer side? They prepare this layout drawing, or it is EPC contractor only who makes that drawing
That
layout.
uh,
SLD developer makes. I know that.
yeah. So this see, SLD will also done by the EPC contractor, but a sketch, a tentative SLD only developer can provide you. But the detailed
Yes.
SLD as a EPC contractor you have to prepare. First of all, second, the control layout the site can provide you, the developer can provide you. Initially, it is the responsibility of the developer to do the investigation to assess that how much land available at their pulling substation, at their solar substation, and that land length and width area they need to provide you as an input. So initially you
Yes.
have to ask to the developer, right? And one more thing, whatever the queries are, whatever the point we have, please let us discuss in that,
I will ask at the end.
yeah,
Okay.
at the end, okay, so that the flow.
Okay, so you are able to finish the question.
Yeah.
No
So
issues.
let us give me 2 hours. Okay, then after that your time will start. Okay, am I clear with the other as well? What the input required. Okay. Second, the available approach route direction to reach the substation site. This also information we required. The third information, we required information about the input power supply feeder to the substation or output feeder from substation to the next substation. is through the underground cable or by overhead transmission line tower. This information also we should know at the layout drawing preparation stage. The fourth input, power supply is through the overhead. If in case the power supply is through the overhead transmission line, then we need the direction and location that could be tentative after transmission line tower, that where the tower is coming, the transmission line tower where they are spotting, also called as dead end tower location of the dead end tower. With respect to the dead end gantry of the substation, I will explain you what I mean by dead end tower and what I mean by dead end gantry later on, after in today's session only. Right. So dead end tower and the dead end gantry, these two locations we require. These two informations required. Dead end gantry is my subsystem, but dead end tower is the responsibility of the transmission contractor or the developer who are making the transmission towers or transmission line, and which is decided based on the overhead line route survey. Okay, so based on the overhead line route survey, here we can see that you can take here that this is my substation site, and here the overhead line route survey have been done. So we know that one tower will come near about in this location, that could be incomer, that could be outgoing, but one line way will come here, and another dead end transmission tower that could come in this direction, that could be outgoing or that could be incomer, anyone. So I will plan that when I will make this substation, this particular substation, I will plan that my line base direction should be towards my overhead line, so that I can easily terminate the line base to the bus bar of the substation, and then I can plan the other equipment direction in line with the line base and the bus bar. So we required this information also at the time of the layout drawing preparation. I'll show you a few example again about the contour layout and about the dead end tower locations with the help of few other example of the drawings. This is a 132 by 33 kV substation. I hided the project name because this is a live running project. So as I told you that you require the information that length, width, area, and the contour layout. So this is the example how the contour like layout drawings looks like. So here the total subsistence area, approach road dimension, and here I have my contour layout, because site could not be every time circle or sorry, rectangle or the square, that could be in any the land could be any in any shape. So what the shape of the land available, they have to plan. So I have to take this as an input, that this is my the land patch where available to do the construction, and accordingly the land availability we have to plan the construction, or we have to plan, or we have to prepare the installation layout drawing for this, for the construction purpose. This is example for the contour layout. This is a like example for the contour layout drawing that you need to ask to the client or the developer. Second example for the dead end tower. So if you see here, as I told you that we required the location of the dead end tower so that we can plan the uh, the location of the substation line page. So here the same contour layout, if you see here, the same. So I took the boundary, I took only the boundary here, and this boundary and in this contour layout, whatever the ground level, all the ground level also marked, so based on this ground level which is marked in the contour layout, how much soil displacement or soil you need to to do the labeling, how much soil you have to displace, this also need to be prepared. This is called as the cutting and filling schedule. that
Yes,
that need to,
civil does that.
yeah, that need to be prepared by the civil team, that how much soil we have to displace the cutting and filling. And if there is huge difference between the land ground level, in that case there would be requirement of the retaining wall, because we cannot make too much soil displacement. It will take the cost as well. So what we do, if there is too much difference between the ground level of the substance, so we can make the substitution between two or three levels, and between each two level we can make one retaining wall, just wall, this wall just to stop the soil that may come on the next level. So to stop that soil, we make the retaining wall. But again, this is the responsibility of the civil department. But again, because you are the lead engineer for the substation, electrical is the lead department, so you must know each and everything briefly. I will try to cover few things with the civil prospectus as well, so that you have the overall understanding about the electrical plus civil. Okay, coming coming to the to this contour layout. And if you see, I have taken this outer boundary only red, black color, and in that boundary I fitted a substation layout, right? So here this red, this sorry, the boundary line, and each boundary line is not straight, so we have marked that 37.56, this from here to here straight, and then 34.39 it is like going this way, and then 62.29 meter it is coming in this way. So all this input marked with help of this contour layout drawing only. Okay, whatever the dimension given in this contour layout. And on this contour layout we like, uh, what I can say, superimposed or imposed a layout drawing. And here I have this dead end tower location position, which is given by the client based on their overhead line route survey. Okay, so they are telling that here they are going to plan. If in case they are planning this tower not here, here, somewhere here, so I have to completely reverse my direction. Am I making the sense? I have to plan in this way, and the line B should be here, so that I can match the dead end tower. Because if I'm not matching with the dead end tower, in that case there would be two or three more tower required. Means dead end tower coming here, line transmission line coming somewhere here, and additionally two or three tower required to meet this line bay direction. So
Yes,
due to that purpose, we when we are going to make the layout drawing, we also should know the tentative information about the dead end tower locations where it is coming. So this is, so what I mean by dead end tower and the dead end gantry. So this tower, which is the last tower of the overhead transmission line, I'm calling as the dead end tower. Transmission line dead end tower, this one, because here transmission line dead, finished, and substation is started, begin. And the last point of my substation, last tower of my substation, last tower and country, I'm calling as the substation dead end country or dead end tower, which here I will show you the means this drawing. If this view you can see here, this view you can see here, I am telling as this is my dead end tower, and here the transmission line is coming, right here, finished, and now entering into a substation compound. So this is my dead end tower, and entering here. So here I have many like gantry and the tower. This is my tower, gantry here, gantry. So this gantry, this particular gantry, this particular two tower, I am calling as dead end gantry of the substation. So the location of the line way, the orientation of the line way shall be in line with the transmission tower. Am I clear? The
Yes.
the
We have to align the dead end gantry to transmission dead end tower. So in the layout drawing, this thing has to be kept in mind.
Yeah, and basically you should have the location so that accordingly you will plan the line bay, the trafo bay, because we have the line bay, trafo bay, bus bar. So accordingly we will plan the position or the location in the service station. I'm just telling you the input, what the input will be required. I'm not telling you this is detail. I'm just telling you the information what you should know when you are when you are starting the layout drawing preparation. So this input also you should know. Yeah, thank you, Amir. That could be only for you, Selva, not for others. Okay. What about others? Am I clear, Ashwin? Am I clear for you?
Yes, sir, you are clear.
So double check your side. Okay. So now coming back. Yeah, thank you, Nikhil. I'm clear for you as well. Coming back. So input is clear. Input is clear. So equipment installation layout drawing. Two drawing. I told you. This is and as I told you, this is both drawing here on the right hand side, and with help of the both drawing, this is a real site construction that done. So how to make this uh, plan and section drawing? For that, what the input information we should have, that input informations we discussed here, the point, and for each point we took the reference drawing. So control layout, this control layout. Then second my underground, second is the directional location of the transmission line towers. So here this is the example for the transmission line tower, this drawing. So when we are making the layout drawing, finally this is my substation and dead end gantry, dead end tower, and from my dead end gantry and tower we have to place here the insulator, and from this insulator we are making connection with the transmission tower cross beams, right? So here we are indicating the connections here, and the distance from the dead end gantry, dead end tower to the dead end gantry is 40 meter here indicated. So this informations also we have to indicate. And and suppose in the case your overhead line route survey is not done, your dead end tower position, your dead end tower position is not decided, yeah, are not fixed. Where it can come somewhere here, it can come somewhere here. If it is the exact location is not fixed, the tentative location is fixed. Tentative location you know, the direction you know, but exact location is not fixed. So when you are making the layout drawing, in that case you have to make the circle here in this, the line side equipment. You have to make a cloud mark on the surge arrestor, CVT, and the wave trap, and you have to write a note in your drawing that the location of surge arrestor, CVT, and wave trap shall be decided based on the dead end tower location. This you have to put under hold. And when you get the tower exact tower their distance from the country and location, and then in that case you can make this three line, and you can show the connection from the surge arrestor, CVT, with the three line, and then this drawing will be fully finalized. Okay, so now coming, so here we discuss the drawing, here we discuss the input what required, and now we are going to discuss about the installation layout drawing preparation. So when we are going to discuss about the drawing preparation, so first of all we have to plan the general planning for the substation. So what could be the general planning, or common infrastructure for the substation? That could be your boundary wall, your boundary wall. What should be their height? Your road, direction into the substation, that where you are going to take the road. As you can see here, one road here, one road here, one road here. So all the road, uh, and then gate, and then boundary wall. And here one information is missing, but you we also have to like make the control room building, and one the security post near to the entrance gate. So this all informations uh, called as the general planning of the substations. So in the overall site installation drawing preparations, we also need to plan the common groundwork or the common infrastructure for the substation, such as road planning, gate planning, boundary wall, stone spreading, etc. Stone spreading, stone in the substation, spreading that we do. Could anyone tell me why stone spreading is important? And and one more
To
point.
reduce
And one more
to
point.
reduce the effect of
One more
step
point.
and export and fuel.
Uh, okay, let me
To
finish.
reduce the effect of
Let me
touching
finish.
step production.
Let me finish. Prithvi, let me finish. I know you are expert, but let me finish. Is it important? Is it stone is mandatory every time in substation? Is it always mandatory to spread the stone in any outdoor switcher? And if so, what should be the depth of?
Not only stone, sir. You can spread anything which has more resistance, which does not allow to pass the leakage current from your body to ground. We use stone basically because it has the high resistance. Resistivity is very high.
Stones will not allow grass to grow.
Okay,
That's
will
the
come
fact.
on that. Will come on that. Will come on that. The stone spreading. And about the stone spreading, we will discuss in detail during the earthing model as well. Okay. So anyway, let us discuss one by one with the stone spreading. So first, let us start with the common compound wall. So once the site land outline is received, yeah, here we have received my outline. This is something in zigzag, right? So once the site outline is received, we need to plan a compound wall for the entire area around the substation line. The compound wall around the substation defines the territory and protect the electrical installation from the theft and prevents any unauthorized entry. Okay, and the compound wall can be made from the brick masonry, stone masonry, or it could be with help of the RCC that could be made. And second, the height of the boundary wall is generally kept at 2.4 meter above the surrounding ground level. So this is a side photo of the compound wall. So the height of this compound wall, usually we plan 2.4 meter, means that height should be more than a man height. So 2.4 meter would be around 7.5, 7.8 foot. So that would be more than a man height. Few client, few utility, few country take this height as 3 meter height. That also considered by a few country specific or the few client as well. Okay, so anyway, so generally 2.4 or 3 meter compound wall height we plan, and height this compound wall could be made by this material. Second, after the like wall compound wall, let us make discuss about the entrance entry gate. So in the same line with the available approach route, we generally plan the main entrance gate for the substation. If you see this particular snapshot or extract of the layout plan drawing, this is the layout as we can see the top view of each equipment, right? Here we have this is here we have, you can see our a road, and then here we have a main gate for entrance, and at the entrance main gate here we have security room that generally planned by 5 by 5 meter. And this gate and road, and this here we have one road again that coming to the control building of the substation. And this, and after that we have again the second gate which is called as a yard gate, because we not authorize each person which is coming in the substation to enter into live substation. So for due to that purpose, we plan one an additional gate which is called as a yard gate. So here we indicate the yard gate, and other area of the substation would be protected by the fence line. Okay, so here we have indicated the fencing, and here also the fencing, and at the road we are providing the yard, the gate to entry into the live yard. So in the same line with the available approach road, we generally plan the main entrance gate for the substations. There are two type of the gate we plan in substation. One, the main gate for entry for all and up to the control room building. Yard gate for entry in switchyard for only authorized person, or that could be any testing commissioning engineer, or that could be any O&M engineer. At the main gate, we also plan the security room around 5 by 5 meter for the security staff that we plan. So again, compound wall and the road is my general planning. And further to the main gate, again we have to make the road inside the substation. So inside the substations means what I mean by inside. So here if you see, I have my uh, main road, right, and then taking entry into the substation compound. Here we have planned the main entrance gate, and after that here we are making one security room, and after that we are planning for the additional route inside this compound. So one road here, one road here. So about these road, so provision of access road and rail track or rail come road should be there near circuit breaker for maintenance purpose, and near transformer and reactors for movement or replacement of transformer reactors. Road width for the transformer and or for the reactor we take 5.5 meter, the width of the road, and road width for circuit breaker maintenance we take 3.75 meter. So coming back to this view, here we have the transformer. So for the transformer replacement, uh, and for to place the transformer here, we need to plan the road near to the transformer, and here we have to make the railcom road, and this road will generally we take 5.5 meter. But that again we have to check, or we have to check with the like what the size of the transformer, but usually we take 5.5 meter road. Okay, so this road is required near to the transformer or near to the reactor. Plus if your case your substation is more than 132 kV, in that case for above 132 kV, the circuit breaker which you can see, this is the circuit breaker, this three equipment. So circuit breaker weight and the size of the circuit breaker is too much high, that could not be handled manually, and we have to take additional like the crane or any erection machine to handle this circuit breaker. For that purpose also we have to plan a route near to the circuit breaker for above 132 kV. Below 132 kV, that could be handled manually. So in that case, this route would not be required. But above 132 kV, the breaker size, weight, high, increase, that could not handle safely with the manpower. We take the erection machine for that, right, or crane to handle the circuit breaker. Due to that reason, again we have to plan road near to the circuit breaker. So this is my internal road which is 3.75 meter, and my main road which is coming to the transformer, that would be 5.5 meter. And if I could not locate here the control room building, and if the near to the control room building, that we can take around 4 meter, or the same 5.5 meter also we can take here, if there is any possibility to like for the transport vehicle which is taking the transformer, that need to pass that road. In that case we can take 5.5 meter. If not, then in that case we can take 4 meter road for the control room building. So I hope that the road planning is clear. uh, coming the compound wall planning is clear, then entrance gate planning is clear, and then my road planning is clear. Fencing, external fencing reduce the possibility of entry to the site by unauthorized person. A special attention should be paid to touch voltage where metallic fencing is used. Internal fencing is used mostly for defining area where access is restricted and generally height 1.8 meter. So as I told you that again we take the internal fencing, so that internal fencing height generally we take 1.8 meter because we are just stopping or just we are defining this is this area the person could come, but in this area the unauthorized person cannot come. So for that purpose we take again the fencing, and for that again we take the gate. So that fencing height generally we take 1.8 meter. And one more thing, if this fencing is the metallic fencing, in that case we have to do the proper earthing of this fencing. We will discuss the earthing of fencing in the earthing module, but I'm just uh, putting because we are discussing the fencing. So if any fault happened, there could be chance to reach the fault current or the GPR of this fencing also high. So we have to do the proper earthing of this fencing as well. Usually at each corner of the fencing, and after 10 meter or few is utility take after 20 meter. After 20 meter, we have to connect this fence with the common ground grid of the substation. Right. That we will discuss later on during the earthing module. Okay, so gate, we have two type of the gate, main gate and the yard gate. Width as per the largest equipment dimensions, that also we can plan. So now the next is the road gate boundary wall. Now coming to the stone spreading. So this is a side photo of the stone spreading. So the final grading and metal spreading and NTV treatment. So in the substation under construction area, the NTV treatment and stone spreading are to be done. The material to be used for the stone spreading is stone aggregate, usually 40 millimeter nominal size of this stone we take, and that stone should, we cannot take each kind of this stone. For that we have some regulations, like in India we follow the IS 383 standard to define that what should be the specification or the type of the stone that we can put in the substation, right? And when it comes to the stone spreading layer thickness or width of the stone spreading, so the final layer of 100 mm to 150 mm thickness. As per for the stone spreading, we can refer the earthing standard, which is IEEE 80. So as per the IEEE 80, a layer of 100 mm to 150 mm thickness of stone spreading of 40 mm nominal size should be spread uniformly over the cement concrete layer. This is also defined in IEEE 80. The stone spreading would, and why stone spreading is required in the substation. So as you all also have told, that stone spreading would increase tolerable limits of stub and touch potential. Stone spreading reduce the growth of grass, unwanted plants, and restrict the movement of reptiles in the switchyard area. We'll discuss this point again, the tolerable limits of step and touch voltage in the earthing module, right? So if anyone could not relate what is the meaning of touch and step potential, so no need to worry. We will discuss in the next earthing module. Okay, but anyway, the stone spreading would increase the tolerable limits. Okay, and as I told that whether stone spreading is 100% mandatory or always mandatory, the reply is that stone spreading is not always 100% mandatory. The substation sites where very low soil resistivity, very low soil resistivity, if we have in the substation site, means the soil resistivity around 4 ohm, 5 ohm, 6 ohm, means what the stone is doing, what the stone is doing here, what the stone is doing here, means how they are increasing the tolerable step and touch potential limit. So let us take one quick example. Suppose here we have the site. On that site we are putting the stones, right? The stones, as you can see over here. And now below the ground, this is the stone above ground we are spreading, and below the ground we have made one earthing grid that we will discuss in the earthing module. I'm just explaining this for your information purpose only, but in the detail we'll discuss in the earthing module. So if any fault happened, if any we have any like RYB phase conductors, and if any conductor is broken and touch with the ground, if any line to ground fault happen, so the fault current will flow into the ground, uh, and this fault current will flow into the common grounding grid. And if there is no any stone, if there is no any stone we have, so there is a possibility that this the the fault current or the potential rise of the soil of the ground due to this fault current G, that may danger to the person which is walking above to the ground. So this stone is increasing the contact surface resistance between the person feet to the ground. So if my this contact resistance is increased, in that case the probability to reach the fault current to the person is very less, and the person would be saved under fault conditions, right? This is what this stone is doing. Is it making some sense? I'm just trying to
Yes, yes,
explain you about
yes, sir, for safety, yes.
the stone is spreading. But if in case your soil resistivity is very less, say 3 ohm, 5 ohm, 10 ohm, very less, so what will happen, your if your soil resistivity is very much less, in that case whatever the fault current is coming, it will not try to reach over uh, uh, to the element or equipment which is placed above to the ground, because my soil resistivity is always too much less. So they will flow always underground. It will not try to reach intend to reach above ground, because this is offering too much less resistivity, and we know the current flow towards less resistive path, and my soil is providing the less resistive path. So why I put the stone above ground? Why I do the extra expenditure to for the stone? In that case the stone is not required. Okay. So our general concept that stone we have to put, but you see that what is the soil resistivity. So stone spreading is not always 100% mandatory. The substation site where have very low soil resistivity in the range of 5 6 10 like that, in that range. So in the event of line to ground fall, the ground potential rise would be very low. Yes, ground potential rise would be very low, because my we know the ground potential rise is what? GPR. Ground potential rise is what? The potential rise means what? V is equals to IR. So I and R is what? The soil resistivity R. So if my R of the soil is very much low, in that case, my current is coming but R is low, so my potential rise of the ground will be low. In that case, in that case in that the ground potential rise would be very low. In this case the stone spreading could be avoided are a very minimum layer of stone, say 50 millimeter layer, means only one stone, each one stone 40 mm, so only one layer of stone could be used to reduce only the growth of grass and reptiles, but not any human safety purpose. Am I clear with the stone spreading concept? Am I clear with the
Yes,
road
sir.
fencing gate, the general planning of the substation, the general common infrastructure planning of the substation, right?
Sir, what is metal spreading?
Where is the matter? The stone is spreading, not matter is spreading.
I think it is given stone spreading, metal spreading, and the anti-weight rate.
Where?
In these slides, sir, if you see the final grading, metal spreading and anti-weight treatment. Heading, sir, heading.
Oh, no, no, no. The stone is spreading.
Okay.
Okay, and anti-weed treatment done just to uh, avoid any growth of grass, unwanted plant. So for that anti-weed treatment done. Okay, so now after the common ground, common infrastructure, after the graveling, yeah, it is also called the graveling. Uh, so now coming to the after the common grounding, after the common planning, let us come to the now orientation of the base or circuit or the feeder. So the line way, we have discussed enough about the orientation, but again let us discuss. Just give me 1 minute. Yeah, too much energy. Okay, so coming to the next planning, and this planning is the orientations of the page. Means where the line bay will come, where the transformer bay will come in this or in this direction, where the bus bar should be placed in which direction. So these orientation planning for the installation layout drawing preparation. So when we will discuss each and every planning concept in the detail, after that we will go to the layout drawing preparation. Okay. So now to the line bay planning. So the line bay orientation or line bay placing should be towards the incoming or outgoing transmission line bay dead end down, which is already I told when in the beginning of the session. So this statement is clear. Coming to the next statement, whereas the transformer bay orientation should be towards the downside voltage level of the substation. For example, in the 220 by 132 kV substation, the transformer orientations will be towards the 132 kV side bus bar. Yes, because we are stepping down with help of the transformer to the another voltage level, and after the stepping down to the another voltage, that voltage need to be fed to a common bus bar, and from that common bus bar we will take the other low voltage line bay. So in that case the transformer should be come towards the my another voltage level, that we can see with this example as well. Here the line bay, as I told, line bay planning towards the incomer or outgoing dead end tower location. So once the line bay orientation done, and then here this is a 220 by 132 kV substation by 33 kV substation. This is this particular sketch. So here if you see this 220 kV with the double main and transfer bus bar scheme, and we are stepping down this 220 kV voltage to the 132 kV. For that we are using a transformer which is placed over here and step down to 132 kV, and now this 132 kV we have to feed to the 132 kV bus bar. So due to that feeding, this transformer bay will be placed towards in the direction of the 132 kV bus bar, so that easily connections could be done on the 132 kV bus bar, and from this bus bar again we can take the 132 kV line bay. And here this is another example for the 132 by 33 kV portion of the substation. So for that again we are using this transformer 132 by 33 kV, and 33 kV step down we done with help of this transformer, and then we are feeding to a 33 kV bus bar. So again this placing will be towards the 33 kV bus bar, right, downside. So the same uh, like this planning, this orientations we have explained here in the test. The transfer bay orientation should be towards the downside voltage level of the substation, and that already we have discussed. So we discussed two bay. line bay, the transformer bay, and now coming to the common bus bar, right? So common bus bar will be placed at right angles. Right angle means 90-degree angles to the feeder. Why? Because we know the bus bar is a common conductor where all incoming and outgoing feeders connect. Yes. So
Yeah, yes, sir. You discussed this point in busbar module.
yeah, already discussed many times in the bus bar model. So this is my common bus bar. Two here we have the two bus bar plus reserve bus bar. So this bus bar we place to the right angle at the 90-degree angle of this line bay or of this transformer bay. So when we place, because this is the common bus bar, common conductor, so that would be placed on the 90 degree so that we can connect each every circuit to this common conductor. Due to that purpose, this should be placed at 90-degree angle for the easy connection of the all circuit. Okay, that we can see here with the, so here we have a transformer bay. This is again side photo, and here we have the line bay, right? So this is my line bay here. If you focus at my cursor, line bay, and we took the 90-degree angles
Yes.
coming here, and this direction is my bus bar bay. So coming here you can see this three conductor is a common bus bar. So here we have the towers, and this three conductor is a bus bar or a main bus bar. Material could be ACSR conductor or could be aluminum tube, right? So if we place 90 degrees, so this can be connected here and this can be connected here. So due to that we place at a 90-degree angle. Let us see with again side photo. Here I have my transmission tower. If you could you please follow my cursor. This is my a series of the transmission tower coming here, coming here. Final dead end tower. This is my dead end tower. Entry to the substation. My This is dead end tower. This is my dead end gantry. This transmission line here,
Yes, sir.
here,
We can follow.
here, here. This is my this particular circuit, this particular circuit, this particular equipment, and
This is a line
the
base.
line bay terminating to the common bus bar, which is placed in this 90-degree
Yes,
direction.
sir.
And then we have this transformer bay, which is again feeding to the common bus bar. And we know the common bus bar is common conductor, but all the circuit means here transformer circuit, here line bay circuit connect common conductor, right? So again a few example. Here we have my tubular bus bar, and then this is my transformer bay, power transformer bay. This one line bus bar here 90-degree angle, and from here I have, this is in this case this is my dead end gantry, and here this line bay is going out. Line bay, transformer bay, common bus bar. Okay. Okay, now we discuss about the common infra. We discuss. Let us conclude what we discussed so far. We discuss about the equipment outdoor installation, that what we are going to discuss. Then we discuss two drawing we require. This is two both drawing, and the near about site construction of taking this two drawing. We discuss what the input we required. This is the example of the input that we required. And then we discuss about the general planning of the surface station. In the general planning, we discuss about the road, fencing, gate, stone spreading, wall height, compound wall height, these things. And then we discuss about the common orientation of the circuits, line based circuit, transformer based circuit, and the bus bar. And now let us enter into the common bus bar conductor material selection. There are many confusion and many doubt as a design engineer, that whether we should take the ACSR conductor, like here I have considered the ACSR conductor, or we should take the aluminum tube. So what is your opinion? Which one is
Yeah,
better?
yes, sir.
Which one is better? The conductor is,
According to me, sir, for about 33 kV system, until we can go for 66, we should use the aluminum IPS rigid busbar system, and for greater than 33 or 66 kV, we can go for the flexible ACSR. Because ACSR is flexible and it is costly, so cost is justified for high voltage.
we have many few other point as well. Let me take the point
Yes,
with the, along with this there are too many other factor.
Whatever I understood,
Yeah, yeah,
that I will tell you.
So we'll discuss in the detail, Ashwin, so that you can make your understanding more wider. Okay, let me take
Okay, sir.
let me take opinion with others as well. What is their thought? Which one is better, the conductor or the tube?
Sir, to avoid the skin effect, we choose aluminum tubular bus bar, and also to allow the thermal expansion and contraction, we use a flexible clamp, and that is very much feasible for aluminum tubular bus bar.
Mhm. Okay, but in that case, if we take the conductor, so that uh, also can be done, because if any thermal expansion coming into the conductor, so there would not be any problem. Okay, no worries, no worries. Prithvi, let me take others' opinion as well. Anyway, I'm going to discuss in the detail with the proper comparison between both. Okay, no worries. Let us discuss. Let us start. Yeah, Santosh. Santosh, this topic I included only for you because you
Sir,
have.
actually, it's also important the space constant. If space constant is more available, then we have to go for ACSR. But in case of we don't have a space constant, then in case we have to go aluminum tube.
We'll
Because
dis-
in that case, can keep phase to phase difference very less. But in the case of ACS, we have to keep minimum more distance between the phases.
Okay, okay.
So
So
I think
Santosh,
for space constant also is important part of choosing the uh, type of material for that line bit.
for the line way, not for the bus bar way, for the bus bar. Okay.
Bus bar, sorry, bus bar policies.
No worries. Let us discuss in the detail and with the exact
Okay, okay. Thank you.
informations, because the information is not this is not the total view. Let us discuss in overall.
Sir, if we choose the aluminum conductor bus bar, in that case, we'll have to design it for short circuit forces, and sag tension calculations are also to be done
Yes.
to avoid that we can opt for tubular bus bar.
Yes, yes. Yeah. No worries. Let us discuss in the detail. Okay. One by one. One by one. Yeah. So let us discuss. This is a very disputed topic. So I have tried my best to uh, like conclude and collect informations to compare uh, between the uh, common with the rigid bus bar and the standard flexible bus bar. So we'll discuss about the common bus bar conductor material selection plus the installation height planning of the bus bar. What should be the height of the installation from the ground? Keep in the mind, bus bar is a common conductor. Bus bar is a common conductor which is placed right angles to the feeders and work as a common conductor for all incoming and outgoing feeders connect. So this is like our basic understanding about the bus bar. So keep in the mind, keep in a corner of mind that what is the bus bar. So let us discuss about the material selection for the bus bar. With the side photo, I'll try to compare two. So this is this side photo. This view is for the this view is for the flexible bus bar, and this another is the rigid bus bar, where for to make the rigid bus bar we are using the aluminum tube as bus bar, and that aluminum tube we place on the post insulator, and that post insulator we give support with help of this support structure. So we are going to discuss about this installation, how height from the ground, plus whether we should go with the flexible or we should go with the rigid, about that. So as we know, in AIS substation, the bus bar might be the flexible type with a stranded conductor made of an ACSR conductor or any equivalent. In place of ACSR, we can go with the other option as well. In SLD model, we have discussed that what the other options is we generally follow, right? Triple AC, if you all discuss,
Yes, sir.
all aluminum alloy conductors. So any
Yes,
any
yes, we
any
are
any
discussing.
any,
Yeah, yes.
any equivalent SSR or any equivalent we can take to make the flexible type bus bar. Or the bus bar could be the rigid type. This rigid type with a tubular aluminum conductor we plan. Tubular, not the solid tube, hollow tube. aluminum conductor. The rigid type leads to a low level type substitution. Low level type substitutions. Height of install is very less, so it leads to a low level type substitution. Plus, in addition, the rigid type bus bar, since the bus bar are rigid with the aluminum tube, so that would be rigid. The clearances remain constant under all situation of the wind speed. So if we have the flexible bus bar, if the wind speed is coming, so there would be swing in the conductor. So when the conductor is swinging, the R phase, Y phase, B phase, suppose your Y phase is swinging, it can come closer near to the R phase or near to the Y phase. In that case, the required face-to-face clearances would not be able to maintain. We are not achieved when the swinging is done, right? How to avoid the swinging? What we do? Anyone could tell me to how?
Dampers,
Spacers.
spacers, yes.
Okay. Anyway, so the swinging will be done in the flexible bus bar. So, but in case of rigid, no space is required. The bus bar is rigid, so clearances remain constant under all situation of the wind speed. One advantage. Okay. So let me add one more point. So if the clearances remain constant, it means between R and Y phase, Y and B phase, the spacing we can reduce. But here, if we come to the flexible bus bar, there would be possibility of the swinging. In that case, the spacing between R phase to Y phase and Y phase to B phase, we have to increase to accommodate the swinging possibility of the conductor. So it means to make this bus bar this flexible bus bar will take much land or more land, whereas this rigid type bus bar arrangement will take less land. uh, I need one or two who can like match with the point. If you agree, if you disagree, anyone engineer or Ashwin, if you can like lead, no issue. So if any substation, if any substation site, now this is the point, and let us come to the substation. Let us implement this point into the substation. So if any substation site is located near coastal area or a site where the wind speed could be too high, the rigid type with a tubular aluminum conductor is preferred over the flexible type bus bar, as due to very high wind speed. If we use flexible conductor, there would be swinging in the conductor and face to face clearances would not be able to achieve. So if your site near to coast area, near to the sea, and are any site which who have the higher wind speed, go with the rigid type bus bar. Due to this purpose, the European country, the UK, US, these country most of the time follow the rigid type bus bar. The rigid type bus bar is mostly used in European countries, UK, USA, because these countries have large coastal areas and generally their wind speed is too much high compared to Asian countries. Okay, and due to that reason, they have more wind power. They have more wind turbine because they have wind speed higher. Right? So they will go with the rigid type bus bar. Rigid type bus bar. Okay, now this is the point number one to compare between the flexible and rigid bus bar. Let us see some side photo. Uh, so here I have my rigid bus bar. Taking the drop on the equipment. Sorry, flexible bus bar. Taking drop on the equipment. The next photo here I have the rigid type bus bar, the main bus bar rigid type, and to make this rigid bus bar I have used the aluminum tube. If you see, this is my tube, and to cover this what I can say, the hole, we used a end cap, right? End cap that you need to consider when you are making the BOQ. Okay, so this is tube that we are making here. Now, but this is not the overall view. Overall, point, we have some other point as well. Further, the rigid type bus bar are not very high from the ground. So maintenance is easy, and due to the large diameter of the pipes or tube, the corona loss is also very less. This is so far the advantage, but there is a disadvantage. But the rigid type bus bar are not suitable for the earthquake prone areas. Why? Due to due to their rigidity. Because they are rigid, if any site or any country where the earthquake prone country or earthquake prone area, prone site, earthquake prone site, at those sites we do not refer the rigid type bus bar. Okay, so for the substation site located in earthquake prone areas, flexible type bus bar with stranded flexible conductor is preferred over a rigid type bus bar. The same concept is applicable for them if we have main plus transfer or reserve bus bar. Means here we have the main bus bar plus the reserve bus bar. So we are discussing for both type of the bus bar. Okay, am I clear? Am I clear with this
Yes.
point as well? With this point, let us do a overall comparison between both. So below table for the brief comparison. So the choice between the rigid and flexible bus bar conductor, flexible type bus bar, flexible type bus bar, most suitable in earthquake prone substation site locations and over the rigid type bus bar. Rigid type bus bar not a good choice for the earthquake prone areas. Flexible bus bar required larger face-to-face clearances to allow conductor swinging due to the wind and short circuit forces. This will result in larger substation areas. Maintain equal rigidity in all directions, which is advantage to withstand wind force, short circuit force, loading, ice loading. So, if in case you have less site, and this is not the uh, earth uh, quick prone site, we can think over the rigid type bus bar. Flexible bus bar required higher structure height to allow the face to ground and face to face clearances due to the conductor sag. In the rigid, there is no sag. Use a large structure than rigid bus bar. Minimum uh, uh, in the tube we have the minimum coronal loss, minimum audible noise, and minimum radial noise. Okay, so this is overall comparison between the rigid and the flexible type bus bar. I hope that this give you more wider in knowledge of the
Mm.
bus bar
Yes, sir.
selection. So now we discuss about the bus bar material we discuss. And now let us come to the next point, which is the bus bar installation height. What should be the bus bar installation height? So when we use the flexible bus bar, in case of the rigid bus bar, in case of the rigid bus bar, I'm not sure that this drawing is too much clear, but if you put a stretch, not so that this drawing is too much clear, but try to focus my cursor. If you see here, I have the support, right? Please follow my uh, and after
Yes, sir.
this portion, this is one trafo bay, and after the just trafo bay, we have again one support. Again, this is not too much clear, but again we have to provide the support over this, and again, sorry, this support is not here. This support is over here. Could you see this support over here? Could you see here? Support,
Yes,
Sir, post insulator.
yeah,
yes,
support insulator, and after the, again this is my line bay, and after the line bay again here we have to give the support again here. So means generally after each bay we take one support if we have any if we have the tubular bus bar, main bus bar arrangement. After one bay usually we take the support, but when it comes to the flexible bus bar, so in that case after each bay the support would not be required because my installation height is above more than the tubular bus bar, and we are using the conductors that is placed on the support structure, proper tower and beam. So in that case the support uh, uh, durations or locations we can increase. So when we use the flexible bus bars means main and transfer are reserved, both bus bar are strung by insulators, called strain insulators through the beams or gantries. So here I have beam. Let me go here. I can see you. So this is my bus bar strung with help of the insulator. Here I have just one second, too much zoom. Here I have the insulator, string insulator, other string insulators. This is my tower, this is my tower, and this I am telling is the beam or gantry. So the flexible bus bar installations with help of the support insulator plus beam or gantry, and this beam or gantry is supported with help of the towers, one here. Okay, and the country is supported by help of the tower at a certain height above ground level. So what height above ground level we take, that we will discuss. Below are a general practice followed for the support beam plus tower locations, as each voltage has different bay width. What I mean by the bay width I will come later on uh, in the after 2 or 3 slide. What I mean by the bay width. So the point is that the general practice for the support beam and tower, as each voltage have different bay width. So the different practices for support beam and tower locations we follow. If in case we have any 132 kV substation, so after each 4 bay width distance, the support beam and tower would be required. Means here one support gantry and tower here, then 1 2 3 4 bay I will take, and after that I will plan the next beam, next support, and then again 4 bay and the next support. If there is only 4 bay, we have, in that case we can plan all the bay in with help of only two uh, uh, gantry, or sometimes if we wanted have go safer side, so we can split between two here, and after that again we can take two, but four is also acceptable. But for that again will depend on the voltage, right? If we have the 220 kV, so after each 3 bay width supports would be required for the 220 kV. And if we have 400 kV, so after each 2 bay width, because in the 400 kV my bay width is increased. For example, for 132 kV my bay width is 12 meters, so after 4 bay means after 48 meter. For the 220 kV my bay width is 16 meters, so after 3 bay means after again 48 meter we are planning the next support. If in case of 400 kV my bay width is 24 meters, so again after 2b means again 48 meter. So again after 48 meter we are planning my uh, location of the next gantry and the tower. This is like how we provide support to the common busbar conductor stringing. This is what we discussed voltage wise. Let us see this example with here. Again again uh, this is my bus bar conductor, bus bar bus bar. Here I have the bus CVT, here I have the beam. This is my here tension insulator beam, and here we have suspension insulator. With help of the tension and suspension insulator we are doing the stringing of this flexible conductor. This is my a 3D view. When we are going to make the layout plan drawing, so in the plan drawing, as I told you that we take the top view only. So this complete bus bar arrangement from the top side, it from the top view, it will appear like this. So when I will come in the drawing, this I will indicate only from this tower, 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 and this conductors. So I hope when you see this bus bar arrangement in the layout drawing, this you can like imagine in your mind this kind of the arrangement. So this arrangement from the top we are indicating like this. I am telling you these things parallelly because when I will come on the final drawing preparations, so the view would be clear that how the view, this view how would be at the site. So this view at the site will appear like this. Now coming to the installation height drawing, installation height of the bus bar. The flexible bus bar installation height above ground shall be as per the below tables. Whatever the height we are going to see, that generally we follow in India, but it may change slightly due to utility and country practices. So please check with the country and a specific project what their practices are, that country what practice follow for the bus bar height. Usually, if we talk in India, so for 33 kV we plan 5.5 meter above ground. For 66 kV we plan 6 meter above ground. Above ground. 132 kV for 132 kV 8.5 meter above ground. For 220 kV 12 meter above ground. 12 meter. This if I take this ground level, so 12 meter above the ground. 400 kV 15 meter above ground. 765 kV 27 meter above ground. This is how we do the stringing for the main bus bars. Okay, am I clear?
Sir, are the same heights value for rigid bus bar also, sir?
No, 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 not, not. I'll come on the next the rigid bus bar. Okay, so hold on. But is when if in case we have the rigid bus bar, so this rigid bus bar looks like this. It appears like this, and if in case we have the rigid type bus bar with a tubular aluminum conductor, the bus bar installation height could be as per the below table. But as I told you during the flexible bus bar, need to double check as a few client may have slightly different height. As I told that the UK and European country follow the rigid bus bar. So if I take the example of the European country and the UK, so we have the national grid as the major utility. Then in UK, and if we go in Ireland, then we have the ESB, Electricity Supply Board in Ireland. If we go in Scotland, so we have the SSE as a main major utility company. So these company may have slightly different height, but usually the height for the tubular bus bar installation for the 132 kV 7.5 meter above ground, which is 8.5 meters, so lower than the flexible bus bar. For the 275 meter 10 meter, for the 220 kV at 275 meter it is 12 meters, so slightly below the their height. And for the 400 kV 12.5 meter, whereas 400 kV we have the 15 meter, so slightly below uh, the ground. Actually, why this installation height we have to maintain, because if you see here we have the equipment, right? Here we have the equipment. So this equipment is also placed on a certain height from the ground. That we will discuss in the next topic. The equipment, but just to give you idea why the bus bar, like how height we decide. So this equipment have a certain height from the ground, right? Isn't it? Am I clear?
Yes, sir.
Plus
Certain height from ground.
from the ground, plus between the bus bar and the equipment we have to maintain the minimum phase to phase clearances. So equipment height plus phase to phase clearances, after that we can plan any main bus bar height. So due to that reason
And height we have to also consider here.
come again ask.
Okay.
Yeah, so anyway, so due to that reason this height of the bus bar come slightly more from the ground, because equipment plus face to face clearances, we will discuss about the clearances as well. Okay, so anyway, but the topic is clear. The common bus bar conductors material selection, one installation height planning, this two topic is clear. About the main bus bar, am I are we clear with the material selection and the installation height and the support?
Yes.
This two.
Yes.
And when it comes to the bus bar, rigid bus bar, let us see again. Rigid bus bar installation support. So here we have the aluminum tube, right? Conductor, which is the aluminum tube, and this is this equipment called as the post insulator, right here. And then this insulator placed on a structure, common structure, where all the RYB3 phase will be placed, and this structure supported with the help of the again support structures plus insulators, on that we place the conductors. And for the equipment, we take the drop from the bus bar to the equipment here, right? So 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 could you, this bar, this loop is for the earthing of this bus bar to fix the earthing clamp, earthing portable earthing rod, so we can place here because this OD of this tube is high, so we cannot easily fix the portable earthing with the conductor. So with here we can place that. So this loop is providing a point for the earthing. Now coming to the installation support. So the rigid bus bar is installed by the support of the post insulator, and these support insulator are mounted on the steel structure till 132 kV single support structure and a common bus bar with three post insulator. Single support structure with a common base. We see this is the common base. This one with three post insulator till 132 kV. Above 132 kV, usually for each phase, because again the phase to phase current resistance is increasing because voltage is increasing. So for each phase, separate support structure and separate support structure with the separate post insulator we usually plan. Okay, so if you see in this sketch, here again, one common structure. This could not be clear, but common structure and then three post insulator. That could be 132 kV, but above 132 kV, like 220 kV, 275 kV, 400 kV, we take individual support structure and individual post insulator as well. Okay, so this is the rigid bus bar support and the rigid bus bar height, and for each bay we provide this kind of support. Okay, and if in case we have the double main bus bar, if in case we have the double main bus bar, main flexible bus bar arrangement, so how that we do? So for that again, we take the separate support structures, separate beam tower stringing we make, then and then we take again the second bus bar, the third bus bar, again we do on the separate uh, support structure and the tower and the gantry. So when we use the double main bus bar switching scheme of flexible conductor, then both bus bar are strung together and parallelly installed at the site. Okay, so now coming to the if we have the bus bar with double main bus bar and transfer bus bar and the reserve bus bar, if this kind of the scheme we have, in that case how we do, first of all the both bus bar will come together. If this is double main and transfer bus bar scheme, so both bus bar will come together, plus the transfer bus or the reserve bus will come near to the entry or exit point of the line bay, not at the trafo bay, at the line bay, right? So in the case of the double main and transfer bus bar scheme, both main bus bar come both bus bar is strung together and separate country, and the transfer bus bar is strung is at exit side of the line bay. Here we use a diagonal or tandem arrangement isolator and a bus post insulator or post insulator to support the equipment interconnection. Conductor are also called as the equipment bus. So this, I think this point I have covered during the SLD as well. Am I clear? I have covered this point during the SLD.
You have told when random arrangement has to be used, isolators.
Yeah.
You told us.
Yeah, so when the tandem arrangement have been used, so that already we have covered during the SLT bus bar scheme as well. So this is a two main bus bar exit. So as I told, the point is that if we have double main and treasure bus bar scheme, so double main bus will come together, but the exit bus bar location, orientation, placing, position will be towards the line bay, not towards the transformer bay, not the towards the transformer. Priority exit line. This is what I'm trying to explain. And in that case we use the tandem isolator or the diagonal arrangement of the isolators for the to reduce the space. Means here we are taking the flexible isolators, a simple arrangement of the isolator, but near to the main bus bar 2 or below the bus bar 2 and below the below the transfer bus bar, we are putting this three phase disk connector in a diagonal arrangement or random arrangement, right? And if by doing this, if the this tube length is this interconnection conductor length is increasing, in that case we can use the post insulator to provide the support of this conductor. Okay, anyway, this has been discussed during the Saturday module as well. So anyway, this is, so we have discussed the planning of the bus bar material, bus bar installation, and how the bus bar we are going to place in the substation. Now let us plan entry or exit of a overhead transmission line into the substation. uh, that how we plan the entry or exit of a overhead line into the substation. So could we take a 2 3 minute break, 5 minute break, then we again start?
5 minutes we can take. Yes.
Okay, so let us start with the 5 minute break. I think Saturday, so I think you all have time. We can again discuss for the next 1.5 hours. There are too many things that need to be discussed, too many things, and then plus the bay width again, the bay width and bay length, depth as well. So there are too many things that need to be discussed. Okay, so we'll meet again after the 5 minute break. I will message.
Okay.